Let's go ahead and get started. Hope everyone is doing well. So today's lecture is going to be somewhat short, and it's going to involve a new topic. So let's go ahead and get started. All right, so today we will be looking at decision trees. Okay. So decision trees are recursive ways of building a tree-like structure to um, decide whether given features will result in a given label. And I think the best way to illustrate that is maybe with like an example. So suppose we have two features, um, x1 and x2, right? And then suppose we have something like the iris data set where there's three different um, labels in that data set. So we can have something like that there, and then so there's blue now for some other. So that's label green, label blue, and then maybe label brown. Hopefully you can see that. So we have these data points here, and the idea, the idea, I guess, here, for these real valued features is to partition the feature space into regions that classify the data. Okay. So, for example, if this measure here was like 0.5, so originally we have this one big region here. So we notice that if we cut the region, the feature space like this, then everything on the left-hand side is now going to be, could be classified as 0.5. So if we have our root node here, and we can say it's x1 less than 5, or 0.5, then if it is, we would classify it as being brown. Okay. Then this is the most pure region here. And when I say pure, we'll get into what that means in a moment. But notice that everything in this region here, say, call this R1, is classified brown correctly. Now, we could have done maybe on the X2 feature or the X1 feature. It just so happened to be that I saw this X1 made the best partition. But then maybe we can say that if this is like 0.4 here for region 2, if we split that region here, so So this would be if x2 is less than 0.4. If it is, then we say that this is green. And if it isn't, we have another region here. So maybe we'll call this region 2, and now this is region 3. And at each time, so we have these pure regions. Everything in R2 is green. Everything in R1 is brown. There is a ratio of the number of correctly classified versus incorrectly classified in a given region. So maybe we could partition again on, say, maybe here, like 0.9. And then we can say if x1 is less than 0.9, we have this region here. So, and you can see that this tree, if we travel along the tree, we're really going from region to region. Okay. So now, where are we? So let's start at the top. So x1 less than 5 is ground. We're going down here. So we're in this part of the plane. And now if x2 is greater than or equal to 0.4, we're in this region here. Okay. And if x1 is less than 9, we're in this region here. And then if x1 is greater than 9, we're in this region here. And the leaves of this tree correspond to the predicted labels that the information will get. And we can stop branching at a given node when it's pure. So like this is a pure region, pure region. Now the regions, region 3 and region 4 are not pure, and we can keep on doing this. And if you can imagine if we just kept on doing this, right? So if I did like here, say it's like 0.7. So if x is greater than 0.7, x1 is greater than 0.7, call it blue. If not, we have another region. And then over here, this is region 4. That's pretty good. We could just stop there and say, we don't want to. The idea is that if we kept on breaking up each of these regions going on forever, we would overfit the data. We would box in every little piece. But the idea is to stop it before we do that. So like here, we have a ratio. So there's 3 total things in there. 2 of the 3 are blue. This could be, we could just say that that's blue. And then here, we could partition that region again, but we could just stop there and take the max ratio. So in that case, that would be blue as well. Or something like this. So this is the general idea behind decision trees. You can also use regression trees. You can use trees to make regression estimates. For example, instead of giving it a label, you would give it the average x and y values from, or x1 and x2 values, take the average of those, and then your predicted value would be that average in that region. Okay, so let's go ahead and show how to use sklearn to do this. Okay. So we're just going to keep it simple, and we're going to do this on the iris data set. So we can say from sklearn.datasets import load iris. And then we can say from sklearn.tree. import decision tree classifier from sklearn. Actually, I'm just going to import tree as well. All right, and then I'm going to load my data. So iris equals load iris. All right. All right, so actually I need to call this as a function. Right there. Okay, let's say that our features are going to be, so let me just see what iris is real fast. So that's the data, target names, feature names. Let's look at just the first two. We'll look at sepal length versus sepal width. All right, so in order to do that, we can just say that features equal to iris dot data, so the access is here, and we're just going to look at the first two measurements. So, yeah. Okay, and then our labels are just the targets, so iris dot targets. Okay. And now to do this using sklearn, it's really simple. We can just say tree classifier is equal to decision tree classifier. Okay. And then we're going to put our max depth. So the depth is how many times we split the regions. So max depth is equal to, say, 4, or something like that. And then we can just train it using the fit method that's common to most of these sklearn functions. So we can say tree classifier dot fit, and we just got to pass it its the features and the labels. Okay. All right, so that should solve it. So now how does this work, or what does it look like? Well, from tree, we can say tree dot plot tree and just throw in our classifier. All right, so you can't really see it that well, but you can say, so if x1 is less than 0.5, and that's true, then less than or equal to 0.5, then we split on that decision. You can't see it, but the measure of impurity is 0.0, so that means that everything over here is correctly one label. And then here we have a measure of impurity of 0.5. Right? And this continues to split until we get these leaves down here. So leaf, 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 that all will give us a classification. So we can say maybe how to predict now by saying, okay, we can just call the predict method. So we can say tree classifier dot predict, and we'll just throw it in something maybe like features 120. So we know that that is a label that it passes. Yes. Okay, so predicted of label 2, and the features, sorry. Target. So we have the Virginicus, Setosa. Virginicus is the very last one. Setosa, versicolor, and then Virginica. We know that this is going to be that label. So it does correctly um, classify that data set there. Let's make this a little bit smaller or less depth. Notice that, so the Gini impurity is the measure at the top here. Here, this doesn't have impurity of 0, but because our max depth was set to 3, so 1, 2, 3, we're not going to split any spaces any further. So if I did max depth 2, so this is just 2 splits, so split here, so 0, 1, 2. So if x0 is less than a 2.5, split here. Otherwise, go over here. If x1 is less than or equal to 1.7, so forth and so on. Okay, so decision trees aren't as fancy as something like neural networks or deep learning, but they're still used quite a bit. They're actually used quite a bit in medical settings to determine maybe like likelihoods or of maybe like heart disease or stroke. So they're an important tool to have as a data scientist to know about them and to know that there are these built-in modules that you can just call as long as you have your target data, as long as you have your features and your labels, you can just throw them in and make a tree that will make these predictions for you. Now, the only thing that you want to be careful about is choosing a depth that's not too far, because if you do that, you're going to overfit your data and it's not going to generalize to out of sample data that new data that you might encounter. Okay. Now, there are probably obvious questions on how these splits are decided, right? How these thresholds and splits are decided. And I'm going to make a separate video going through the mathematics of that. I just wanted to make sure that today I just showed you how to just run this on a given data set and understand what the output is saying. Okay. Also, from last time, the error that I wanted to mention this before I forget, that plotting error that I had, I just fixed it by using linspace and then plotting that same function that I made, the predictor for the quadratic regression problem. So that was the only thing I needed to change, and then I got this nice line here. Okay. So I'm going to make a separate video on the mathematics of the splitting, so that if you wanted to try to program this from scratch using Julia, you could try that. Otherwise, I would just say use the built-in functions and find a data set of your liking, and look up a little bit more on decision trees and create a small notebook for that topic. Okay, so honestly, I think that's going to be it for today, because I do need to make these other more in-depth videos for you. So that'll be it for today. However, are there any questions regarding your notebooks, regarding your repositories? We're coming towards the end of the semester, and I still don't know where all of you are regarding your repositories.
Is there a day that we should basically have or to send to you before the final semester? That way, because I know you say you want to check on them.
Yeah, I just need you, some of you still haven't done it. I still would like to see all of your GitHub repositories. So if you haven't already sent me a link to your repositories, please do so. And then once you send them to me, I check on them periodically. And because the semester is coming to an end, if it's not to a certain point yet, I'll probably contact you and see if I can help finish out the repository. But I still just need to see, as soon as possible, all of your repositories.
Okay, thank you.
Okay. All right, I'll post this short video on YouTube. And again, if you haven't sent me your stuff, send it to me, and then we'll meet again on Wednesday. Y'all have a good day.